Okay, everyone. Hopefully we can start back now. This is into the discussion session that will run until 4:20 Eastern. And this is on novel gravitational wave studies. It's a very open-ended topic, and hopefully we'll have some good discussions around it. So the brief of the session itself, I've expanded a little bit, and it's not only the latter two, the gravitational wave search opportunities afforded by NGXX, and then whether we can tune our observance strategies for gravitational wave targets. But I also wanted to highlight the novel, quote unquote, novel searches that are happening right now. And things that I would classify as novel are anything beyond our vanilla approaches in the gravitational wave searches, which makes it quite an expansive definition because one could even put advanced noise modeling and variations of our existing searches under that umbrella. But things that we do hope will be given by new search opportunities in NGXX, DR3, and then future data sets would be things like constraining the turnovers and needs in the spectrum that were talked about earlier. So the turnovers give us information about dynamical interactions of the supermassive black hole binary population. The needs give us information about the discreteness and the finiteness in the population. But there are also things beyond just the spectral shape that we could probe in the future. If we have enough information, we could assess stationarity of the background. There's been a lot of conversation in other PTAs, particularly the PPTA, about stationarity of the signal. And stationarity would have the influence of coupling our frequency bins together. So the frequency bins in the spectrum are no longer independent. And one could imagine that would happen if you have, a few eccentric supermassive black hole binaries. Eccentricity is going to cause the gravitational wave emission to be distributed amongst harmonics of the orbital frequency. So the signal is no longer monochromatic. It no longer necessarily falls in one frequency bin. You could have the same binary contributing to multiple frequency bins, and that's what couples those bins together. Likewise, if you have just, parabolic encounters, that could lead to stationarity as well. Obviously, we hope that our newer data sets will gain more information about the spatial correlations to allow us to probe anisotropy using whatever basis or whatever set of techniques are developed. So there are lots of techniques out there, ultimately all trying to use information in the spatial correlations to make maps or find excess power in the background. When it comes to new physics, there are lots of active searches going on for early universe signals. I'm not going to summarize them all here. I'm sure there are people from the new physics group that can talk at length about this, but there are a huge number of searches going on, and those early universe searches don't even scratch the surface of more expansive searches, like looking at beyond GR theories. So beyond GR theories could be probed by PTAs by looking for extra polarization states of gravitational waves and also looking at propagation effects. So if the gravitational waves in other theories don't necessarily propagate at light speed, then that could show up as modifications to the spectrum of spatial correlations. So effectively, the Hellions and Downs curve gets deformed, and we get a different version for sublight propagation speeds and a different version for different polarization signals. In addition to those beyond GR searches, there are dark matter searches, both for cold dark matter substructure and then ultralight dark matter, that's sometimes also called fuzzy dark matter. So these are all things that I would classify as novel, not in a kind of a way that is meant to be diminutive of these searches, just that they go beyond the kind of initial searches that we do with our pipeline. Initially, we're just searching for something that is a power law, something that is correlated according to the Hellions and Downs curve. And that's all that we have evidence for at the moment. And so we would hope that as we go to newer data sets, that the additional information in the time series and the additional information in the cross correlations would allow us to probe many of these things. In my opinion, the most important thing we need to address through the development of these new techniques and deploying these new methods is proving the origin of the signals in our band. And I think we should consider very hard how we can prove to ourselves the origin of the signals. Consistency of the spectrum with models is great, but I think it's still a weak proof of the origin of the signals in our band. Likewise, finding a monochromatic signal that happens to be correlated, or that we can't tell the difference in how it's correlated, is a weak sign of a continuous wave signal. Do we need evidence of the pulsar term in order to really tell that this is a binary gravitational wave signal in our band? These are the kinds of criteria we'll need to develop in any kinds of continuous wave task force. But in general, how are we going to tease apart possible signals in our band? Given that there's huge spread across realizations in supermassive black hole binary populations and large theory spread as well in these new physics spectra. How do we prove to ourselves, and therefore how do we prove to the broader community what we actually have? Now, some people have very nicely added some slides that we can run through. I think the first one is on anisotropy, but this is very open-ended. So if people have comments on anything on this slide or want to add their own content, we can definitely pivot and come back to that. But in the meanwhile, I'll just start on slide 4 here, which is anisotropy. But please feel free to contribute if you'd like to, either in the Q&A or just live, if you have thoughts about the types of new searches that we can do with our upcoming data sets. So first of all, anisotropy. And I think Nihan, you added this. Do you want to talk through some of this?
Yeah, I won't read everything on this slide, but essentially this anisotropy, I think, is something that will be very crucial to address exactly the point that you made, Steve, which is we need to tell what's causing this background signal that we see right now. And there's really 2 flavors of anisotropy that could come in our data set, depending on what the source signal is. One could be astrophysical, so these would be our supermassive black hole binary systems. But if this signal is not from supermassive black hole binaries, then we would expect the signal to be more cosmological in nature, and there we would expect it to be more isotropic rather than anisotropic. So at least I haven't seen any models coming from the new physics literature that predict a strong level of anisotropy coming from that family of models. So that in itself, I think, gives us a strong way to distinguish between whether something is astrophysical or cosmological, at least for the background. And then if we do indeed start picking up hints of anisotropy in there, maybe that can help us lead us to our first single source. If we have some part of the sky that's nicely localized in our anisotropy searches, maybe we can use those as priors for our continuous wave signals. On the other hand, then that also leads us to the question of when do we say that we haven't seen anisotropy yet? So we have to say that the background that we are seeing is mostly isotropic, and that would naturally go on to rule out supermassive black hole binaries as the source of the background. Is there such a point that we would come across? And then do we pivot at that point to thinking that the background is from a new physics model? So I've just tried to collect my thoughts on some work that's already going on with respect to some of these, and then some just ideas that I've doodled onto the slide. So if people are interested, please take a look. But yeah, I really think we should start focusing more on anisotropy in the background, because I think that will be really interesting and help us distinguish between the different sources proposed for the background.
Yeah, thanks a lot, Nihan. And of course, this is sort of technique agnostic. We just need to look at this a lot more and develop the sharpest techniques to investigate frequency-dependent structure in the background. Is there anyone from the new physics group here that can speak to whether anisotropy is actually expected from cosmological signals? Ken, yeah.
I don't think it's universal completely that cosmological signals are completely isotropic, but almost all. You kind of have to search hard to find some model that would not lead to an isotropic background. Of course, isotropic is isotropic up to cosmic variance, so there's going to be some anisotropy anyway. But I think it's a reasonable distinction if we can. I mean, there's another question here, which is how good bounds can we get from a given amount of data on isotropy, and is that the best way to try to distinguish this? So far, our ability to determine anisotropy or isotropy is pretty weak from the data that we have.
Right. Yeah, that's a good point. I mean, yeah, going back to something that Nihan mentioned before, I think you would have to constrain the lack of anisotropy to some ridiculous degree to try to prove that it's cosmological sources. I think the prior odds on this being astrophysical are very large, obviously difficult to quantify. But if you keep ruling out anisotropy to smaller and smaller levels, I'm not sure at what point, you could actually go to the broader community and say, well, we've ruled it out to this point. Now it clearly has to be some sort of cosmological signal. I still think that's a weak argument, even though you might have constrained it to some very small degree. Nihan?
So we tried to do a little bit of this with the 15-year anisotropy paper, right, where Amico made these excellent simulations to sort of come up with pessimistic expectations for what the anisotropy would be, conditioned on the amplitude we saw in the 15-year isotropic background. So something like that could sort of serve as a guidepost as to say if our constraints, given whatever basis you choose to use, are below those thresholds, then we really need to start thinking about whether this could really be from supermassive black hole binaries. So something like that, I think, informed by holodeck or the astrophysics working group efforts would go a long way in that sense.
Sure. But in I suppose the devil's advocate position is inconsistency with supermassive black hole binaries equal to consistency with cosmological signals? Because I think that's not the same. And if anything, inconsistency with supermassive black hole binaries points to some problems within our pipeline or our statistics before we would feel confident that it really is cosmology. Ken?
There's also the issue of smoothness of the spectrum, which most but not all cosmological sources have. So at some point you could say, black hole binaries should have excursions, as Andrew was talking about earlier. And if we don't see them at some level, of course, it's hard to say, this is too smooth, just like saying it's too isotropic, but that would also be a sign of black hole binaries not being the source.
Yeah, that is a good point. And I think the fact that the level of anisotropy is predicted to increase with frequency, equivalent to saying that the fluctuations in the spectrum increase with frequency as well. That is a strong prediction, I think, of a binary population, and something that if the fluctuations actually conform to our expectations based on population modeling, that is convincing, I think. Okay, I'm just looking at the chat here. Yeah, thanks, Joe, and thanks, Bensei and Nihan. Yes, Michaela, go ahead.
Sure. I mean, I haven't looked at CW much in the past, but wouldn't consistency between a few CW detection and the level of the background that you observe be a very strong argument for supermassive black holes? I don't know if this is outside the scope of this discussion here, which seems to be mostly on the stochastic, but once we have a few right detections, they will be coming out of the same population, and you should have an argument there, as LIGO is beginning to have, right? They don't quite see a stochastic background yet, but it shouldn't be too far for them. And then it becomes a continuum of good detection, threshold detections, and then the rest. So it will start with few bits of information and evidence, but that would be convincing to me.
Yeah, I agree. And this session doesn't have to be stochastic entirely. Continuous waves are welcome. Yeah, I think I'm not quite sure how you'd formalize the argument yet to say, you know, we've got a stochastic background, now we have something that looks like a continuous wave from a binary, ergo the background had to have been from a population of supermassive black hole binaries. But I think that statistical connection can be made and would be convincing. All right, do we have further thoughts on anisotropy at the moment? We can always come back to it. Okay, I think I'd like to jump on to the last slide then, because it's another example of a novel search that is almost ready. And this is search for generic gravitational wave bursts. I presume this is Bensei and Healing and others.
Yeah.
Who would like to talk about that?
Yeah. I guess this is as novel as it gets. So I think we are pretty close to getting started on searching for these unmodeled generic gravitational wave bursts in the 15-year data. And one nice thing that I think we'll have is that we'll have two independent pipelines to look for these. One of them is led by Helling, this piecewise linear model, and the other one is a wavelet-based model that Jacob and Rand is currently working on, and me and Neil worked on it before. And Jacob and Rand actually had a talk about that tomorrow, if you're interested. And I think that's really good, because when we look for these, you know, like totally unexpected kind of sources, there's really no best approach to model them. So I think this will be really powerful, that we'll have two different pipelines to compare results with. So yeah, I guess I just wanted to say that this is happening, and we will keep updating people as we start with this and start to get results. And I think at some point we may want to collaborate with the Astro and New Physics Working Group, maybe to see, you know, if we get any upper limits, how we can interpret those in terms of various kinds of signals. And I am also expecting that maybe some advanced noise modeling might be important for this one too, because unlike the background or maybe even continuous waves, there are mostly like low frequency stuff. These might be like time localized high frequency stuff where we could be picking up on kind of noise transients buried in the data that we didn't know about yet.
Right.
So yeah.
Nice. And what are the signals that have been injected into these plots? Are these really just like sine Gaussian bursts recovered, or something like that?
We did that too, but I think what is shown on these plots is this like hyperbolic encounter of two supermassive black holes. I think that's the most physically motivated source that we can think of.
Yep. Yeah, and that's something again that I've heard people talk about as inducing non-stationarity. If you had a small number of hyperbolic encounters dominating at low frequencies, that might actually be picked up as non-stationarity. Who knows? I think it's worth searching for these, since the signal model is not that complicated anyway for a hyperbolic encounter.
Yeah, that's what I wanted to say as well, that I was just thinking about this the other day, that these generic burst things feel potentially pick up these hyperbolic encounters. But if you think they actually might be out there, then actually searching for them with the actual waveform that they have, like an actual search for directed at these hyperbolic encounters, that might be interesting as well, because that will always be more sensitive than a generic search. So I don't know how much of a prior expectation we have about these, but yeah, we could definitely do it.
Right. Bit of NANOGrav history. And is Dusty on the call? Because I'm probably going to mention the burst with memory from like 2015 or 2016. There was a time in 2015 or 2016 when it looked like there was a memory signal that appeared in our data, was consistent with our data, and we really pulled out lots of different types of searches and noise models to try to mitigate this. In the end, it looked like it was sort of absorbed by more flexible noise models, just free spectral intrinsic red noise models, and it was very close to one particular pulsar on one side of the sky, which was very fishy. But as part of that as well, we tried changing the antenna response function from a quadrupolar one to a dipole one to a monopole one, because there you're not just trying to recover the shape of the signal in the time series, but also how it's effectively manifested in the different pulsars. And you can imagine just doing a little hypermodel analysis where you have it switch between monopole, dipole, and quadrupolar antenna response, and actually showing that it obeys an antenna response pattern that's quadrupolar. That surely is the key evidence of its gravitational waves. So I think that's a novel aspect we haven't really developed yet for our search pipelines, but you could imagine it would be incorporated pretty easily. Yes, Rutger, it really did mess with us. It seemed to agree with quadrupolar pattern. And I'm right. I'm correct in my recollection that it was advanced noise modeling, or what we called advanced noise model at the time, that got rid of it. I think it was free spectral intrinsic red noise plus localizing it to being one problem pulsar. Oh, Yilling, thanks for this reference. Let me pull it up real quick. Yes, of course. Yep, it's got IPTA members that have led it. Excellent. Okay, so this is already happening. Okay, how about we switch over then to this idea of to tune or not to tune observance strategies for gravitational wave targets. Jeremy has very kindly put in some material from his talk yesterday. Jeremy, would you mind just summarizing your slides again for everyone?
Mute yourself. Okay, can you hear me?
Yes.
Okay, awesome. Yeah, so I'm in the room with Ian, so I'm speaking through his laptop. So basically, these slides are showing a hypothetical campaign that we tested. And so maybe one thing that I didn't emphasize enough yesterday in my presentation was that we simulated PTA for this. So it's really supposed to just be a methods thing. And our plan is to take the NANOGrav 15-year data, simulate it into the future, and see if we can come up with some like real hard recommendations for tuning specifically the NANOGrav PTA. And so we would really love to see like a lot of collaboration on that, because this is sort of like a very big like collaboration wide decision, right? It affects everybody from like timing to detection to new physics and astro. So I guess the more like input we could get on that project, probably like the better the project is. But one of our sort of findings, which isn't necessarily new, like we've kind of seen this for like in a few of the papers that I referenced yesterday, but it's that we could very easily sort of change around our cadences and our PTA to get basically free sensitivity at high frequencies, right? And that's something, I guess, Steve, you asked yesterday, like, how long would it take before that sensitivity kicks in? And that's something we would need to investigate. But probably like the sooner we sort of like do something like this, the better. And one of the, I guess, goals of this project we're proposing as well is to specifically look at like, well, when we get access to the DSA 2000, like what kind of choices can we make with that to really like optimize the sensitivity we can get with this like new telescope, right? And so there's a bunch of like open questions there. But yeah, I guess the key takeaway is that we could dramatically improve our high frequency sensitivity, not only to continuous waves, right? But I've been talking to Bensei about this, and we're pretty sure that that would be very beneficial for generic burst search as well. And for that matter, any gravitational wave background that would be at high frequencies. So I'm not very involved with new physics, but I'd imagine that that would help constrain some region of parameter space that we're not currently constraining. Yeah, so essentially these plots kind of just show that.
Thanks, Jeremy. So yeah, that's this talk of improving sensitivity at higher frequencies is very interesting, and I wanted to get people's thoughts on that because personally, I'm a little bit scared of higher frequencies because of the kinds of binary pulsar effects that happen beyond 1 over a year. And I was going to call on Caitlin anyway, and so I'm glad that she put her hand up because she can speak directly to this. Go ahead, Caitlin.
Yeah, I was just gonna say exactly what you said, Steve. It's scary up there. I guess with a positive spin on this is if we do think that we want to go after higher frequencies above 1 per year, there's a lot of space up there that we're sensitive to. And there's a lot of benefits to using those higher frequencies. Like in some searches, that power law turns in our favor. And that's really good. But there's a lot going on up there that we don't understand. So we would need to, at the same time, devote a lot of effort to methods development to make those searches run fast enough, be able to identify what is actually going on so we don't end up going down leads that we then can't actually identify.
I totally agree. Michaela?
Yeah, so it's not the cadence that gets you the added sensitivity here. I think it's just the SNR, because you're timing the better pulsars, and therefore you have less white noise. So if it's differentially more sensitive at high frequency, it must be because of red noise, I guess, is limiting the limiting factor at low frequencies, and that's where you win with white at high. Because if you're looking for a monochromatic signal, actually, the way we do with we're not limited by Nyquist theorem because we don't have equal time sampling and so on. So at least that's how I understand it. So tell me if I'm wrong. But that also means that we need actually to have nice white noise out there. And as Steve and maybe Caitlin were saying, the free spectral runs that we published are a jungle up there. So that's why we only use 14 gravitational wave frequencies for the background, because if you use a couple more, you pick up everything there. So it would be nice though. It would be nice if we could understand things up there. But I don't know that simulations are telling you really what's going to happen, just because they assume clean white noise effectively. So, yeah.
Thanks, Michaela. I think Jeff was first.
Yeah, I think these are all good points to be made. I think that on this plot on the left, though, there's the red dashed line. There's higher than the red dashed line, but then there's the green line too. And It's not shown here in any of these plots, but in some plots that Jeremy showed yesterday, we still get large improvements in the frequencies sort of higher than the bucket and lower than the 1 per year spike, where the effects that you all are talking about are much, much less than above that. Also, if we're worried about binary pulsar issues, then we get to pick, right? So 1909 doesn't have a binary period that's anywhere in the range of this plot. So if we keep hammering on 1909 or pick some other pulsars that are either appear to be solo, not in binaries, or have really long periods, then we might be able to avoid those things too. I think, and then on top of all of that, there's the advanced noise, right? So custom noise models are getting us more and more sensitivity without doing anything at the higher frequencies. So I mean, I think these are all good points that we need to keep in mind, but I don't think it's a reason not to look up there. And as we go, the background is just going to be more and more in our way at the low frequency end. It's always there. We know it's there. So we can get gains at high frequencies and we don't lose. I think the point really to hammer here is that if we don't get rid of pulsars and we just go to lower cadence on those pulsars, then Kelley's right. It's the RMS change that is really, well, it's not the RMS change. It's the power and the white noise, right, which is dependent on the cadence and the RMS. That is where the gain is from. Sorry, I was in the middle of a sentence there, but anyways, I think those are all good points. But again, we don't lose sensitivity if we just go to lower cadence instead of no cadence in those pulsars. So it's really a win. We get more sensitivity up there. And if it ends up being work for noise, then there's a lot of us who have made our careers doing it. So there's plenty of work to do there.
Yeah. Thanks a lot, Jeff. Nihan next.
Something that I think we should also try and take a look at is how these changes in our observing program would also affect our searches for anisotropy. So very roughly at sort of the first order we showed in the paper that I had with Steve and Joe, that essentially you want as many pulsars as you want, and you want your uncertainty on the pairwise correlations to be as small as you want. And so you can link that back to your cadence through Harvey scaling laws. And so there, essentially, there's also going to be a trade-off, right, between how many new pulsars we can add and how well we can improve the uncertainties on our cross-correlation measurements. And so I think it would also be useful to try and connect how these changes affect our searches for anisotropy. I just don't know. I haven't thought of a good way of doing that yet, but I think it's something we should also keep in mind.
Agreed. Thanks, Nihan. And Ken.
So I haven't looked at actual signals versus actual sensitivity or what we could have, but naively, this seems extremely helpful for new physics. If we could get better sensitivity at higher frequencies, because many new signals have smooth spectra that extend to very high frequencies. Black hole binaries would dissolve into discrete lines at high frequencies, so it would be easier to tell them apart. And also, about the only hope of distinguishing one new physics signal from another is through the spectrum. And if you want to distinguish things by their spectra, you want to have as much reach as you can to get into different frequencies where the spectra might be different.
Yeah, thank you very much, Ken. And we've only got a few minutes left, but I think, Jeremy, did you have a second slide or was this someone else?
Yeah, this is also my slide. And so I guess I made this last night based off of one thing that came up yesterday when we were talking about quote unquote going all in on the IPTA. And so this is something that Jeff and I have talked about before, but some people were saying, well, what would that look like going all in on the IPTA? But the idea here is sort of that like NANOGrav has a lot of pulsars that we have like a pretty decently long time span on, right? And so rather than us with like, say, the GBT or something, doing these like high cadence observing campaigns, what if we just got like a next generation telescope like Mir time or like fast to do these high cadence campaigns? because we would only need them to do these high cadence campaigns on like shown here in this plot on the right is just for like up to a dozen different pulsars. And so the idea is that they would have better sensitivity to these pulsars to begin with, right? And so if we give them these pulsars, they're going to do a much better job at these high frequencies than we will with our telescopes. So we just keep observing, you know, like as we have been, and then we would sort of bring in the long time spans and the associated gains with that, while these telescopes to the so maybe not Meerkat specifically, but you know, this idea of like a next generation telescope that's sort of dedicated towards these like high cadence campaigns, right? Because they basically would see through a lot of the white noise that we get with our radio observations, right? And so this could potentially lead to even greater gains at high frequencies, as shown in the plot, whereas we would do the work of sort of like really characterizing the background, which, you know, Nihan was saying is important for anisotropy, and I'm sure is very important for a lot of like astrophysics associated with the background. So that's just like an idea. It would require obviously like a huge buy-in from you know, the IPTA, but if we're thinking about something like this going forward.
This is a really cool thought, Jeremy. I never thought of like having different parts of the IPTA potentially tuned to different parts of the spectrum. And it almost reminds me a little bit of the Einstein telescope concept for ground-based, where you have like an above ground part of it and a below ground part of it, each trying to mitigate different parts of noise in the ground-based gravitational wave spectrum. It would require a lot of buy-in, I agree. And the timeline of Meerkat, I think, has been pointed out as well, even though I think the incredible results that we're hearing are coming out of Meerkat might give it a longer lifespan.
Yeah.
But this would require a level of connection, a level of coordination in the IPTA that would be a real step up from what we have at the moment. It would need a lot of coordination.
Definitely. I guess like exactly what you're saying, though, it's exactly the idea of like we just let each sort of collaboration or each telescope really play to its strengths, where one of our strengths is this longer baseline, whereas their strength is the very precise like TOA error, right?
Yep. Interesting. Well, it feels like we could keep going and keep talking over ideas, but I think we might be at the end of the session. Is that right, Seven, or anyone else?
Yes, 4:20.
Okay, so we're at time. Thanks, everyone. Let's keep this conversation going, because I think, as I mentioned at the start, I think one of the really key questions that I would like the collaboration solve is prove to me and prove to each other and prove to the world where these gravitational wave signals are coming from. And if it's a statistical argument, as in based on the statistics of the population, that's fine, but it needs to be a really strong airtight argument if we're going to claim that this really is supermassive black hole binaries. And it needs to be even stronger if we're going to claim new physics, obviously. Okay, I'm going to stop sharing. I think there's a 10-minute recess, and we can keep the conversation going on Slack. Thanks all.
Thank you, Steve. We'll pick up a few minutes after 4:30 with the cross-working group discussion led by Luke and the rest of the astrophysics group and others. Thank you.
Okay, well, Thank you all for joining. So this session is the interpretation of gravitational wave results. So there are a few topics that I want to go over with this panel, in addition to hopefully having lots of questions from the full audience. So I think the kind of main topics here are multi-messenger astrophysics, simulations of sources of gravitational waves. This doesn't necessarily need to be restricted to the binaries astrophysical side. This could include some of the new physics side of things. And then the kind of inference and interpretation of gravitational wave results, particularly the background, but this could also be upcoming continuous wave sources or other features, anisotropy and whatnot. So before we actually dive in, I wanted to open up to any questions from the previous discussions or talks. Following the discussion yesterday or today, are there any kind of hot lingering questions that anybody wants to raise from kind of the astrophysical or general sources modeling perspective?
Are you asking the panelists or everyone here?
Both. Very much both.
I have a comment. I guess I can share it here.
Yeah, please.
I don't know how we can categorize this, but I don't think we are prepared for beyond GR searches. I think this is the part that maybe the broader community does it better than us, or faster, or more efficient. We have this alternative polarization project that it's very difficult to do because of the lack of personnel, and Dallas did a very good job of combining everything together. So he spent just many days on his own doing this, and the same thing happened to me a few years ago for 12.5 years. And I feel like we are having the same, we have a script and we just keep changing the data set, but the script and the methods are the same. And I'm wondering if anyone in the detection working group or the broader group in astrophysics or beyond physics actually has ideas on how we can do more or do better for beyond GR stuff. Maybe not necessarily just the alternative polarizations. And maybe we can do a lot more. And I'm wondering if people have ideas or are willing to actually spend time, maybe do methods development before we get very busy with IPTA and the new NANOGrav data set.
Yeah, great question, Nima. Alexander?
Yeah, hi. I do trying to do a little bit of testing GR things a little bit on the back end. It's a bit of a pet project of mine, and I will be talking about 2 such studies tomorrow during the poster session. There's one where I've made use of the post-parameterized Einsteinian formalism in 2 different ways. One to look at deviations from GR with the stochastic background, and another parameterizing deviations in the generation of continuous waves from supermassive black hole binaries using continuous waves. So sort of one of each way to go about doing it. But again, progress is pretty slow, as with Dallas. I'm kind of just like, again, it's like a pet project. So it's just kind of, it's something I'm working on the side, but slowly working my way through over the past, I don't know, year and a half-ish kind of thing. So I'll talk a little bit more about this tomorrow, but I know there are a couple good discussions happening, at least in the new physics working group. Every now and then it comes up, I don't know, maybe every other month on telecons or so, that somebody's doing something. But yeah, it is few and far between those of us who do tests of GR and beyond GR kind of work.
Great, thank you for sharing that. Any other thoughts from anybody? I guess one follow-up question I have to that is, are there any places where we have an edge over something like LIGO, which is mostly and kind of more of a strong gravity regime?
Preliminary results indicate yes, certainly for negative PN terms with the background. But I need to do more work before I actually can give you a definitive answer on that.
Yeah, I mean, this seems like a great question in general, Nima.
One more, since you asked, look, we are more sensitive to the vector polarization modes, but they are a nightmare theoretically and from a practical point of view to search for, but on paper we should be more sensitive to them than LIGO.
Okay, and is the complexity and the
Sorry, why is that, as someone who doesn't really know general relativity?
So the vector modes, the correlation pattern at a small angular separation for us, the correlation pattern is huge. So if we find pulsars that are very close together, and we look at the overlap reduction function or the correlation signature between those pulsars, if the vector polarization modes exist, they should just show themselves, because it's just the correlation strength is huge. So if you Harrington Downs is the baseline at 0.5 is the correlation value, these are orders of magnitude higher. So we should be able to see them, but this is on paper, by the way. Doing this actually, developing methods for it, looking for it, and making sure it's not something that we're picking up that is just random noise is very difficult. That's a difficult part of it.
Yeah, great question. All right, let's move into talking about multi-messenger astrophysics. So I'd like to ask the panel, what are your opinions on what the most important existing electromagnetic observations are, either single AGN, single galaxies, or dual or binary AGN or candidates? What are the most important ones? What should we be comparing against or thinking about? I'm going to bump Kaihan to go first.
Sure. I think people in the Astro Working Group know this. Maybe not everyone does, that I am a big skeptic, almost to the point of cynic, in terms of electromagnetic candidates for binary AGN or binary systems. So I am very pessimistic about any chances of finding a continuous wave signal source that is also an electromagnetic source, for the reasons that there won't be a lot of continuous wave sources. The probability of them being lit up as AGN is already low, and then there is the sky localization just makes it very hard to that point. If there were a lot of binary AGN easy to find, we would already have found them, and then we would just say like, oh, which one of these is it? So I'm not convinced that looking for them looking for AGN signatures is the best way to go, because there is we're not able to pull the signal from the noise. I will now yield the floor to Laura, who will hopefully lift everyone's spirits.
It's almost like we've had this conversation before, yeah. So yeah, I'll chime in with my usual voice of I guess relative optimism. I think that first of all, if indeed it holds up that the 15-year results are pointing towards short in spiral timescales, and that points in the direction of it being more likely that there is gas around the black holes while they're in spiraling in the gravitational wave band. So obviously that comes with all the caveats that we don't really know what the binary characteristics are yet, but if this hint holds up, then that's, I think, pushes it in the right direction. Another possibility is that, we're seeing a strong signal. All right, Joe says more tomorrow. That we're seeing, a strong signal because we're on the cusp of resolving out one or more continuous wave sources. In which case that bodes well for, having the chance to actually try to identify the host and the counterpart. I do think it's going to be difficult to localize, just figure out which host
just by looking at galaxy catalogs, not that we shouldn't try, but that's probably going to be tricky. But I think that if we can place a strong prior on AGN in a particular part of the sky, in a particular redshift range, then that combined with all the time domain data we're about to get from Ruben gives us some hope for trying to actually find perhaps even a binary AGN signature that we can't we wouldn't have necessarily picked out as like the lowest hanging fruit just with electromagnetic sources alone, but the combined prior of the combined data from the gravitational wave and the electromagnetic light curve or what have you might give us something that we can actually pin down. So I don't it's definitely not going to be easy, but I do have more optimism than Kaihan.
I do love the optimism. Laura, you mentioned that if we're right that systems merge quickly, you're more optimistic that they'll have a high gas content. Could you explain that a little bit?
Yes. Good call. Again, we have these sort of insular conversations in the Astro Working Group. So the idea is that if you have the astrophysical environment that we know has to drive these binaries together, if it's doing so in an efficient manner, such that things get to the gravitational wave regime pretty quickly after the binary forms and becomes a gravitationally bound binary, then it's likely that whatever gas got funneled to the center of the galaxy during the merger is less likely to have either been accreted or blown out through AGN feedback processes before the binary gets to the gravitational wave regime. So there, as opposed to the scenario where if you have a binary that gets to the parsec separation and stalls for a couple of gigayear, and in the meantime the gas in the nucleus all is accreted or forms stars or is blown away through feedback, and you just have this cell binary in a mostly collisionless system, then you're perhaps less likely to have an associated EM signature.
Great, thank you.
Could I continue? One thing that if it's all right, one thing that if we believe our astro models, and right, we're the people who worked on them are taking them with the biggest grain of salt of all, we're also seeing black holes that are 10 to the 9.5 and larger mostly, and merging around redshifts of 0.1, 0.2-ish. I don't think we have a lot of gas-rich mergers happening in those giant galaxies, though, do we? So is it reasonable? I guess they're in the PTA band at 0.1, 0.2, and so they could have merged earlier, but it's still not, if they're quick merger times, it's still sort of in a gas poor merger dominated time of the universe. Am I wrong about that?
You're saying around redshifts of 0.1, 0.2, right? Did I hear you right?
Yeah.
Yeah. So I mean that is definitely a consideration that the most gas rich mergers are going to be happening at higher redshifts on average. But again, whatever mergers do happen are going to have it, major mergers are going to have a tendency to drive gas to the center, their centers. And so it may not, even if it's not a gas rich merger, if there's enough gas in the nucleus, you don't need an enormous amount of gas, right, to have an influence on binary evolution. So I think there's that, and then also the fact that if indeed binaries inspiral efficiently, maybe that's because binaries that we see in gravitational waves in spiral efficiently, it's because gas is in fact playing a role in that. And so maybe there is some other population of stalled binaries that we're not seeing. But the ones we see, maybe gas is playing a role.
One thing that I'd like to add is just we should be careful about the distinction between not being any gas and not being cold gas, which is what a lot of the observations and our kind of conventional wisdom about dry mergers at lower redshifts and higher mass galaxies. And that's not necessarily one-to-one mapping to plausible activity in electromagnetic signatures. So the next topic that I really wanted to bring up was, what is the role of kind of triggered searches, in both directions? So we think we have a continuous wave source in the gravitational wave data. We want to look for electromagnetic counterparts, or what a lot of people are already actively working on is taking electromagnetic candidates and looking for gravitational wave signals. So what are the approaches that we're missing that we should be doing differently? Do we need to reevaluate this if we're very skeptical about the existing candidates? Maybe I can put Joey on the spot for any thoughts.
Sure, yeah. This is an important point, an interesting question. So one of the things to think about is that I think we've done pretty well, is to think about these same kinds of questions in the other bands for gravitational wave astronomy. So what do people that are working on LISA and space-based detectors, what are some strategies that they're trying? What does LIGO do? Now it's not the same. And we do have good overlap actually between the communities, especially when you're talking about analysts, data analyst people. So I think I'll just start off with saying, I think those are some good places to look, to think about what are people thinking about in the other bands.
As a LISA and LIGO expert, do you have any kind of initial thoughts?
Well, so targeted searches in our gravitational wave searches certainly improve our sensitivity when you can constrain at least several of the many parameters, then it helps in that range. So those are the things that I know about, right? Where you can just sort of put in, if you know location and distance and masses and things like that, then it just improves your search sensitivity. Yeah, so that's at least one thing that we can do.
Any comments, thoughts, or questions from the crowd on the topic of triggered searches?
I do have something, Luke. This is Zavin.
Yeah, please go ahead.
Thank you. Since we released our stochastic background results last summer, I've been approached, and probably others have too, by several people claiming to have a favorite candidate electromagnetic periodic signal that they would love to see if there's any evidence for gravitational wave emission in NANOGrav and other PTA data sets. And they've come from all electromagnetic wave bands. There's been a gamma ray person, there's been an X-ray person, there's been a visible candidate. And this, I know this is simplistic and naive, but the one thing that occurred to me, and I've spoken to a couple people about this already, would be once we feel that we have the necessary computational tools in place, it would seem like a good move in terms of accessibility to the community, and something that NSF might like to see happen, if we had something like an online calculator where anybody could submit right ascension, declination, and orbital period, and turn and have the crank turned somewhere to produce an upper limit maybe, or something perhaps stronger. And it wouldn't even have to be our latest and greatest PTA data. We wouldn't want to scoop ourselves, but for example, if we backpedal one release, so if we had a tool now, for example, it might use the 12.5-year data set instead of the 15-year data set, and we'd make that kind of thing available after we have done all the analyses that we would like to do. But I take Kaihan's point and mostly agree with it, that there are a lot of claimed periodicities which don't have enough cycles and which are probably actually quasi-periodic to be credible. But I just wondered if that kind of making that kind of facility available to the community is appealing to anyone.
Yeah, very interesting. I think Caitlin probably has a response to that question before we go to Ken.
Yeah, I was just gonna say I've been kind of looking for a good response to that question for a couple of years now, and I've kind of been soliciting that question from EM astronomers, because otherwise we're not going to build that community. So I'm really glad that you've had people ask. And I always try to be encouraging when people ask me this. But I think this is something that we need to have a firm group answer on, especially by the time LSST starts, because like more and more people are going to ask us this, because we are more in the forefront of people's minds. And like, we need to like be united on the front about like what the rules are, what we actually want to do, and how all of those projects would look. And I will say, like, I certainly would love to see an online tool where people could do these runs. I think, one unfortunate reality is that the continuous wave searches end up needing a lot of babysitting. So like, I think the idea of doing something that runs on an older data set is a good idea, but I don't know how predictable the results would be if it's like a full continuous wave search that people are able to like put in points and distances and go. And I would be afraid that, some sampling issue would come up and people wouldn't know how to recognize it. So I think that's a good thing to play with, but I don't know the feasibility of it immediately. I think it would take work.
Thanks, Caitlin. I guess I would have thought that, so some of your previous results show that you only need to know the frequency to within a relatively large factor. And because we have intrinsically poor sky localization, the exact position also shouldn't affect things too much. So I guess I would have guessed that we only needed to search 10, 20 different frequencies at 100 different sky positions or something like that. And then that is the entirety of the data that we need. Is that incorrect, or is that still computationally very challenging?
I mean, I don't think it's incorrect. I think it's probably would be, if that's the way we'd want to go, the more efficient thing to do would be to just, publish the multi-frequency sky maps that like Bensei produced for the 15-year continuous wave search. And I think that's very reasonable. Whether people want to be able to search and target their specific candidate versus the whole batch of sky, I do think like there will be some like sensitivity averaging. It depends on where things are, and it depends on what frequency features are included within that band. But I think, thinking quickly, I think nominally, yes.
Yeah, well, it sounds like, first steps might be pretty feasible. Patrick, do you have a question or comment on this exact topic?
I do. It looks like Ken's hand was up before me, but I'm not sure what his point was. But
yeah, go ahead, Patrick.
Okay, thanks. Yeah. So one of the things that we've thought about within LIGO in the past, and maybe people have thought about this here, are joint EM gravitational wave searches where, so one of the things that we thought about and was never actually published was, for example, looking for gravitational waves from a pulsar in a low mass X-ray binary where you don't necessarily have evidence for electromagnetic pulses in the X-rays because you don't necessarily have the sensitivity, but simultaneously looking for pulsations in the X-rays while also looking for gravitational waves, and looking at both of these things collectively. If, for example, the pulsations are happening at the same frequency, could boost your sensitivity in some respect. I don't know if this is something that people have thought about for NANOGrav as well, using things like AGN light curves and some sort of joint likelihood. I feel like someone told me that this has been thought about, but I don't know. I don't know if that's a thing. So I figured I would just mention it. Yeah.
Yeah, I think that's a really apt comparison. Yeah, I mean, definitely, using candidates, AGN periodicity candidates for gravitational wave searches has been performed, but I'm not sure about kind of doing simultaneous searches where you're kind of assuming that something is sub-threshold in both gravitational waves and the EM side of things. That's interesting. Any other? Yeah,
can I finish on that? I think Jeff Hasboon was interested in looking at this, but I don't see that he's on right now.
The chat is being very illuminating in this.
Oh yeah, okay.
Maria has worked on this, and Caitlin as well. So
great. Yeah. Yep.
All right, let's go to Ken. Thanks for your patience.
Sure. I want to ask a question about the frequency of electromagnetically identified candidates, because I think a lot of people are coming here to us with periodic light curves, and the better precision we have about what we're looking for, the better job we can do of finding it, because the less evidence we need if we're looking in a very narrow place in sky location, of course, as best we can, or in frequency space. But earlier today, there was a lot of discussion which seemed to amount to, well, even if we think it's periodic because we have a light curve, we shouldn't trust the period at all. So I'd like to understand how big a deal that is, because it seems like if we can't trust the period, we give away a lot of our sensitivity.
Panelists?
I would say, and I didn't catch every part of the earlier sessions today, unfortunately, but I would say that I wouldn't make a statement as strong as that we can't trust the period at all. I think that if there is truly a periodic signal coming from a binary black hole, an EM periodic signal, it is likely to have some relationship with the period. It may not be exactly the same as the binary period, but I don't think it's likely to be completely random either.
So harmonics or nearby frequencies?
Could be either, I think, is what I've gathered from the theoretical literature, unfortunately.
Nihan, go ahead.
I'm sensing a lot of skepticism about detecting these individual signals, or at least it'll take us a long time to confidently say we detect one. So maybe a slightly cheeky question is, maybe we can just detect all of them with this amazing new thing called anisotropy, right? I have this one hammer and I'm finding it nailed to hit it on, right? So what I wanted to ask was, has there been significant work done on trying to predict what kind of spatial distributions these supermassive black hole binaries are expected to have? Because what I'm thinking is, if we do have some kind of idea about what it looks like, we can use that as a prior for our anisotropy searches, and then that can sort of help us do a targeted anisotropy search. So I wanted to see what thoughts you folks had on that.
Yeah, so one of our main experts on this is Emiko Gardner. I don't think she's on right now, but do any of the panelists want to respond?
You're in the best position to summarize her work.
Yeah, so the idea is generally that we believe that sources are most likely to come from large enough volumes that large-scale structure is not really important. So it's very likely, although I don't think this has actually been quantitatively confirmed, that you can assume that the sources are distributed uniformly in space with some redshift dependence. So in that case, you just have kind of independent points distributed throughout on your sky. And that's something that you can model and basically just depends on the distribution of strain amplitudes. That's really all you need to know. So you do still get very different results depending on your model parameters. So for example, EMICO has shown that if you tend to have higher masses, fewer higher mass systems as opposed to more lower mass systems, you'll tend to have more bright sources and thus more anisotropy. So for kind of all of the different parameters in population models, you can kind of play a similar game and understand which direction it should go in. And of course, you end up with a very messy parameter space overall. Andrew, did you want to add on this topic?
Yeah, I actually just wanted to since you mentioned that while we don't think large scale structure should really be relevant here, but hasn't quite been quantified, this is actually basically the next project that I'm going to be working on. In fact, I have anisotropy map, like simulated anisotropy maps on my other monitor right now. But basically, for anyone who's not familiar with, this touches on some of Chiara's 2017 work, where she took a all-sky galaxy catalog from 2MASS, just going out to 225 megaparsecs, but used those galaxies to probabilistically assign mock binaries and then calculate gravitational wave skies based off of that. So my next project is to extend that work out to, we're aiming for a redshift of about 1, which is a much larger volume and should let us actually quantify whether or not we actually see large scale structure or should expect to see large scale structure or not.
Great. Yeah, thanks for adding that, Andrew. And I'm glad somebody's really going to push on this direction. Nihan, did you have another follow-up?
No, I think it got answered by what Andrew said. So broadly speaking, we don't expect to see large-scale anisotropy because of, say, clustering of these supermassive black hole binary sources, but it should rather show up as smaller scale, pixel-level anisotropy.
Great. Okay. So we only have.
We should have an expectation for what the 2-point correlation function of that is, right? I mean, or we should be able to calculate that, right? I mean, maybe it's just the number of expected things that the number of binaries we expect to be able to see divided by 4 pi steradian is just basically what we're expecting then.
Great. Okay. Great questions. So unfortunately, we only have about 5 minutes left. So I do want to pivot a little bit. Let's think about how we're actually drawing inferences about either astrophysics or about, particle physics or cosmology. So for both the panelists and for the crowd, what are we doing right so far? What might we be doing wrong? What are things that we could be missing? Are there synergies or opportunities, again, connecting with something like the LISA community or with the neutrino or high energy particle communities that we should be further exploring? Nima, do you have any thoughts?
Not specifically. I was thinking how I was going to ask a question from everyone here, because the status of the detection working group as of right now is that almost everyone is working on methods for doing things better, doing things faster. I've noticed that a lot of people use KIFL because it's a very powerful tool now that connects with the efforts of the detection working group to the other working group. I was going to ask this question: is there anything for the inferences for the astrophysics working group, for example, or the new physics working group, is there anything that you guys want from us? We're working on KIFL, we're improving it. William is specifically working on that. I have my own project as well, which I'm going to talk about tomorrow. Is there anything else that's missing that we can help with? This is the best time to ask because everyone is working on methods or thinking about methods.
Yeah, great question. Panelists? Honestly, from my perspective, I can't think of anything offhand. I think we have the constraints that we need. There's a lot of work that we need to do on the astrophysical modeling side to just improve and update our models, and then huge challenges in just the parameter spaces that we need to explore. But the other panelists, any other thoughts?
Nothing really jumps to my mind at the moment either. But I will definitely let you know if I think of something.
I agree with you, Luke, that we want to speed up our models. Holodeck is the bottleneck in terms of speed right now, anyway, for our searches, for our inferences.
So maybe to push on possible synergies a little bit more. So we talked about connections to LISA or LIGO for electromagnetic counterparts, but what about more broadly? There is one project in the Astrophysics Working Group to try to make predictions for LISA massive black hole binary detection rates. But are there other good avenues where we can apply our tools or our science to potential sources? What about sharing techniques like are our challenges in decomposing the gravitational wave background and continuous sources? Is that similar to the global fit problem with LISA? Is there opportunity for sharing techniques there?
Yeah, there's definitely noise modeling expertise and techniques that are useful. And then the burst type searches are also across the bands a good place to look. But you're right, and going the other way to share things that are developed in NANOGrav and the PTAs with other collaborations. Those are at least two other examples.
Yeah, absolutely. Great point from Steve in the chat about what about astrometry? And that's Steve, do you want to go ahead?
Yeah, it's just a quick point, because I think there's still a lot of interest, maybe even like growing interest about looking for gravitational wave signals using perceived astrometric deflections in either stars or AGN. And there's even a cool concept of correlating timing offsets and PTAs with astrometric deflections, and the overlap reduction functions, the equivalent for the Hellions and Downs curve, is all completely analytically treatable. And I think it would be interesting to take some of our technical advancements we've done in data analysis and try to apply it there. It seems like a really, really difficult problem to take cross correlations of either billions of stars or millions of AGN. But on the theory side, people have just started looking at like if you took the PTA signal that we have now and project that into astrometric detectors, so you could do the analysis, what would be the signal to noise you would get? And for Gaia, it's something like 1 or 1.5. But then there are future missions that are not like decades in the future, but still in the future, that could achieve a signal to noise of a few. And maybe you could lower your false alarm threshold a little bit on an astrometric detection if you use the knowledge that the signal is already in the PTA band and has been discovered. So I think it's an avenue that we should consider, because it's right between PTAs and LISA, and there is an overlap with the PTA band.
Yeah, absolutely. I love that. In addition to making LISA predictions, we should be making some astrometric ones. And then based on how promising that looks, we can see how we could piece together some of our constraints or some of our observations. Any thoughts or comments on astrometry in our last negative minute? Okay, well, thank you so much to the wonderful panelists and to excellent questions, comments, and additions from the crowd. I hope everybody has enjoyed the fantastic presentations today and is ready for tomorrow. Any closing comments, Zavin?
Just thank you to you, Luke, and to the panelists, and we will reconvene at noon Eastern tomorrow, 9 a.m. Pacific. Thanks, everyone. See you then.